Of course, this is going to be week 5, lecture 1, as I promised in class that I was actually going to make a recording of, of the lecture that we have today. Okay, so give me 1 second. I'm basically going to share my screen. Okay, give me 1 second. Okay, I think I'm sharing that now. Okay, now the title is basically probability distribution of continuous random variable. This is basically going to be taken from chapter 4 of the recommended textbook. Of course, before now, I've walked you through the probability distribution of, of the discrete type. Of course, we got 2 types of random variable. We got a discrete type, we got a continuous type. And of course, I've walked you through the probability of a discrete random variable. One of them is Bernoulli, binomial, hypergeometric, and the like. But what we want to start now, we will basically want to focus on continuous random variable. Of course, when you have variable, when I talk about continuous random variable, we got a lot of, measurement situation that can actually be modeled by continuous random variable, because of the fact that in the continuous random variable, we got 2 main characteristics. Okay, the very first characteristic is just that, okay, the possible values, cannot be counted. And another main characteristics of continuous random variable, the moment you basically want to compute the probability of a continuous random variable, lying in an interval, all what we're going to do is basically to find the antiderivative of a given function, and that very function is going to be called a probability density function. Okay, so in the outline, of course, like I said, I'm basically going to walk everyone through how to, the understanding of a continuous random variable along with their probability distributions. Okay, so I'm going to start with the continuous probability distribution now, looking at the continuous random variable x. Okay, so when I'm talking about random variable x, okay, we're actually going to use a function that is basically going to be called a non-negative function, okay, that we call probability density function. Okay, in the case of a discrete type, okay, we call that function probability mass function. But for continuous random variable, it's basically going to be called probability density function. Okay, now because I said, we talk about a continuous random variable, we're actually seeking to compute the probability that that particular random variable S lies in an interval AB. Okay, so that is what we actually, if I want to find the probability of a continuous random variable, because a continuous random variable cannot be expressed as a whole number. Okay, so what we can actually seek for is to be able to figure out, what is the probability of X lies in the interval. Okay, so this is a graphical representation of what I just talked about now. And of course, this is actually, in an integral form. I told you the other time, I'm seeking to find the probability of X lying between A and B. Or what I'm just going to do is to integrate, a probability density function over the range of over what I'm going to call the state space of S, which is going to be from A to B, as you can see. Okay, so I'm actually going to start with the definition right now. When you actually have, a function, okay, and that very function, is basically going to be qualified to be called probability density function for continuous random variable X. okay, if that f of s is actually non-negative, okay, what I mean here is basically, non-negative, okay, and this guy means for every x lies in real number, okay, what I guy means. Now I'm trying to say for every x lies, okay, in real numbers. That's exactly what that means. Okay, I needed to take notes of that. So which means if I actually plug in the values of x in real number into the function, okay, we shouldn't have a negative. That is exactly what we mean. Okay, here. Now, another basic property of the probability density function is when I actually integrate the f of s, okay, over the range of a negative infinity to positive infinity, of course, which is going to be the entire state space of, of a random variable x, that actually, follows, that's from real numbers. Okay, so at the end of the day, that's going to integrate to one. You remember what we did the other time when we're talking about, probability mass function, which is the function for discrete random variable. What we always do is to say summation the probability of s equal to a realized value is going to be equal to 1 over the state space. But right now, okay, when you're talking about the continuous one, okay, we basically the integral sign is basically going to replace the summation sign, okay, and all we are just trying to tell the world that is the total area under a curve is basically going to be equal to 1. Okay, so when you look at number 3 now, what am I talking about? What I'm actually talking about is, okay, I want to find the probability of x lying between A and B. I needed to take attention now to this. This is close at both ends. It doesn't really matter. Okay, so whether it's close at both ends or not, I'm going to say this guy is also the same thing as, when I have A less than X, less or equal to B, it can be open at here, close there. It's still going to give the same thing as, having this guy now less than B, and also going to be the same as, when they are open at both ends. Okay, so what I'm trying to tell the world right now, I'm still going to use this on each of that. Okay, situation whereby x is continuous random variable. Okay, all of that, they're going to be equal. But you know what? In the case of a discrete, they are not going to be equal. But for continuous random variable, they're basically going to be equal, for every A, B lies in real number such that A is less or equal to B. Of course, we expect A to be less or equal to B. Most of the time we want A to be less than B. So of course, this guy is going to be the lower end point and this guy is going to be the upper end point. And the moment they are equal, of course, you expect to get 0. Okay, so take a look at that. Okay, the more information is actually here. We are still talking about, continuous random variable. We're looking at the property of a function, or, which is actually a probability density function of a continuous random variable. So what we're talking about here, number one, is that, in the case of a discrete, where we can actually find the probability of s equal to a realized value. For instance, I want to find the probability of s equal to 3 or equal to 2. Okay, in the case of discrete, that can actually be found. But when we're talking about continuous right now, okay, we cannot equate f of s to this. You remember when I was walking you with discretized probability distribution, I was actually using this, right? For discrete, I remember when I'm talking about Poisson distribution, for instance, it's basically going to be exponential raised to power minus lambda raised to power x over x factorial. Whether I want to write for Bernoulli, I want to write for binomial or hypergeometry. If I want to write for discrete probability distribution in general, this is what we always write. That's what we always use. But we don't use that when the x the random variable now is continuous. So instead of using that, we're basically just going to use f of x. Okay, take note of that. And number two here is basically trying to say the probability of a continuous random variable would be equal to an exact value. Okay, that probability is going to be equal to 0 in the case of a discrete case. Of course, that is going to exist. For a continuous case, that is going to be equal to 0 for any a rise in the number. And of course, I actually demonstrated number 3 the other time when you're talking about continuous random variable. All of that, they basically going to be equal, but for discrete case, they are not going to be equal. And all of this is basically pointing into that. So anytime you're giving data, exactly what you're going to do. Okay, so when you look at number 4 now, it's just trying to say we can actually figure out the probability of x lies in a set. Okay, we're talking about this as a set now. Okay, now the the boundary here is basically going to be the state space of that particular set. Okay, so I'm actually going to move now. Okay, so what I'm trying to display now is, if you take a look at this guy, you're basically going to see that every area, every space is shaded on this curve. Okay, now if every shade is shaded on this curve, then it means I actually, I'm interested in the total area under a curve. Okay, now which is basically going to be, I want to integrate f of s, okay, using the entire range of real number. Okay, what I'm trying to tell the world now is that x lies in real number, which is going to go from negative infinity to positive infinity, which means I've considered the lowest in this world and the maximum in this world. And of course, I expect that to give me 1. Okay, the 1 here is just talking about 100%. So which is more or less talking about the probability of a sure event. You remember in class the other time I talked about that. Okay, so here now I'm not interested in shading all of that. We're only trying to find the area covered, between A and B. Okay, we expect the result that we're going to have here to be less than 1. And when you come to this side now, I'm only interested in something that happened, from B and above. Okay, B and above. B actually start from here, right? And of course, the area of this shaded portion is basically going to be the probability of s greater or equal to b. And if I want to use integral now, it's basically going to be that I'm actually going to start from b, and that is going to go all the way, oh my god, to infinity f of s ds. Now what about this guy? Now I'm interested in the left part of the curve, starting from A, I'm actually going to the left. Oh my God, I'm actually starting from A. If you take a look at all of this now, it means the situation is that, okay, we're starting from negative infinity and we're basically going to find ourselves in A. So that's why you see our negative infinity to A. So what this guy actually depicts now is the probability of S less or equal to A. But there's something I want us to take note now. Okay, in the case of this guy, it's basically the same thing. Okay, if it is open at both ends, okay, or I mean this guy now, okay, whether it is open here, but I mean close here and open here, it doesn't really matter. Just take a look at that. And when you take a look at this guy as well, okay, for continuous random variable, we can also do x less than a. So that's the same here. For continuous random variable, I can also do x greater than b. So it's basically going to be the same. Okay, so take a look at all of that. So that's what we have. So what I want to do at this time is basically to give an example of how this actually work. Okay, so I told you the other time that continuous random variable can actually depict measurement situation. Okay, we find ourselves in a stochastic world. We live in a probability space, and of course, we expect that we're basically going to have record errors because of the fact that our model cannot capture exact reality. Okay, so if you take a look at this example now, suppose that the error in the reaction temperature in, degree, for a control laboratory experiment is a continuous random variable X having the following probability density function. Okay, I'm going to explain the meaning of this, what I'm trying to tell you now. Okay, we got that this probability function, and of course the state space of X is going to be -1 to 2. So what it's trying to tell the world is that when error is made, okay, in the reaction temperature, for those of you who actually conduct a chemistry experiment in the lab, biological experiment in the lab that has to do with the reaction temperature, of course the error that can be made has already been mathematically modeled as 1/3 S squared, and where the possible values the error can take, based on your experience in the laboratory, actually go from -1 to 2. And of course, the meaning of this is that when I'm considering, outside this range, okay, we don't expect the function to be defined. That's why the function is equal to 0. Okay, so we basically, the question number 1 here now is verify that the f of s is greater or equal to 0. We said it the other time. One of the properties of a probability density function is that for every X in real number, we expect this to be non-negative. And of course, we can actually verify that. And what this guy is trying to say, before this can be regarded, as a valid probability density function, okay, when I integrate this guy now over the range here, okay, I'm not going to use from -infinity to infinity. I'm actually going to use the range given in the problem that must give me 1. And, from there, I can also figure out what is the probability of a random variable S, lying between 0 and 1, even though I'm actually giving from -1 to 2. Okay, I'm basically going to verify number 1 now. Okay, so if I want to verify number 1, I can actually verify, using graph. When I actually plot, days, okay, this against days, okay, this is what I'm actually going to have. Here, I told you the other time, it doesn't really matter, okay? This guy can also be, we can rewrite that as days. That's no problem for continuous case. And that was why I'm actually choosing from -1 to 2 in the graph. Take a look at that. Choosing from -1 to 2. When I plug in -1, of course, the fact that this is a quadratic, this is an S square, right? Okay, whatever value you choose, whether negative or positive or 0, is basically going to be non-negative. So which means graphically, we've already verified the non-negativity of the function X. Okay, so and that was why I said here, of course, the f of s is basically going to be greater or equal to 0 because the f of s is actually quadratic. Okay, so if you want to investigate, the other one, okay, you want to investigate this guy now to see whether the total area under a curve is basically 1. So what are you going to do? Okay, so what you basically going to do is, if you take a look at the formula, I basically want to go from -infinity to infinity, right? Okay, now, if I really want to start, I'm basically going to start from -infinity to -1. Don't forget, we actually, this is actually starting from -1, but you know what? If I go from -infinity to -1, that is outside the range given, that is outside the range of this guy. And of course, anything outside the range is basically going to be 0. When I make use of a -1 to 2, which is the realistic part, okay, the one I circle now is a realistic part. And when I go from 2 to infinity, that is also falling outside the range, and that is why that is going to be 0. So the most realistic part is the one in the middle. And of course, what I'm basically going to do is to perform the antiderivative on that. So when I have negative this to that, 1 over 3 s squared ds, of course, you're basically going to have 1 over 3 -1 to s squared ds. And of course, if you integrate that, it's basically going to be that 1 over 3, and you're actually going to have from -1 to 2, and 3 times 3, that's going to be 9. And that was why you're actually having this guy. So all what you're just going to do is to plug in 2 and plug in -1. You're going to subtract them, and that's actually verify the fact that the total area under a curve is basically going to be equal to 1. Okay, so you can go ahead and, trying to depict that graphically. When you're trying to depict that graphically, it's more or less like going from -1 to 2. All of that is shaded. The total area under a curve is basically 1. So take a look at that. Now I can go ahead and make an inference. Okay, making an inference, I actually know that the state space is going to go from -1 to 2. But what if in a situation where I want to find the probability of X lie between 0 and 1. Okay, don't forget about what I said the other time. Okay, this guy can also be this, less or equal to that. Less or equal to that is going to be the same. Or I'm actually going to have this less or equal to that, or less than 1. And I can also have a 0 less than S less than 1. Oh my God, you're still going to use the same approach. Is going to go from 0 to 1. It doesn't really matter whether it is open at both end, close at both end, open at one end, or close at the other end. It doesn't really matter when you are actually referring to S as a continuous random variable. Okay, so when you do that over the range, that will give you 1 over 9. Okay, so if you want to look at a graphical representation of what we just did now, even though we actually have the entire range from -1 to 2, but we're only focusing on 0 to 1, so which is going to be from here to 1. So the area cover now is 1 over 9. If you really want to make sense of what we got now, you can actually multiply this by 100 in terms of percentage. What you are trying to tell the world. If you multiply 1 over 9 by 100, let me say 1 over 100 over 9, so that we can actually make sense of all of that. So 100 divided by 9, so that's going to be 11.11%. What does that mean? It's trying to say the probability, it's trying to say 11.11% out of the time, okay, when the error is made, that error is going to be between 0 and 1. That is what it means. Okay, so I want to go into another definition now that I'm actually going to call cumulative distribution function. Okay, if I have a random variable X, okay, whether discrete or continuous, okay, we can actually figure out cumulative distribution function. Okay, whether you talk about the probability mass function, which is a function for discrete random variable, or you talk about the probability density function, which is actually a probability function for continuous random variable. We can actually figure out the CDF that we call the cumulative distribution function. So if the probability function, whether the PDF or the PMF, because if they actually have a lowercase f, okay, the CDF is basically going to have an uppercase. I needed to take note of that. So what I'm trying to tell the world now, if I basically want to find the CDF, okay, an uppercase F as a point S is going to be the same thing as a probability of S less or equal to X. Okay. And what is the integral implication of what I just talked about right now? The integral implication, what I talk about right now, if I want to find the probability of S less or equal to S that I actually call CDF, okay, so this is basically going to be, I'm going to start from the negative infinity, and that is going to terminate at S, but I'm not going to write f of S anymore. I can replace my X with any other variable. I can just say f of t, okay, dt. Okay, so what I have now is actually the CDF of a probability density function. Okay, so what is the essence of the CDF? If I calculate the CDF, okay, do you know we can also use CDF to compute the probability that a continuous random variable is basically going to lie between an interval A and B. Okay, so when you take a look at this guy now, if I want to find the probability of X lie between A and B, okay, I can rewrite this guy as the probability of the upper one, less than the upper one minus the probability of that. And you know what? This guy is the same thing as f of b. So which means if I derive the f of s, all what I'm just going to do is to plug in b to replace s. Okay. I'm also going to do the same here. Okay. This guy is actually for that guy. So which means if I derive my f of s, which is my CDF, an uppercase, or what I'm just going to do, if I want to find the probability of X lie between A and B, or what I'm just going to do is to plug in place of S, to plug in the uppercase, to plug in the lowercase, and I'm actually going to subtract that, and basically I'm going to figure that guy out. Okay, so we want to go back into example 4.1, and you know what we want to do to example 4.1? We basically want to find the CDF, and after finding the CDF, okay, we're going to use the CDF now to find this. The other time we find this directly, right? Okay, the idea of the CDF can actually be used to also do that. Okay, so I want to go back into the function or given initially, and what I want to do now is basically to figure out how the CDF that we call the cumulative distribution function. Okay, so if I want to start, I'm actually going to start outside the range, okay, outside the range, which is going to be for -1, for X less than -1. Okay, you take a look at this guy can be written as S greater than -1, S less than 2. Definitely this guy is outside, okay, it's outside the range given. And when you talk about outside the range given, what do we say? X squared is going to be 0, right? And that is why this guy is going to be 0. So for X less than -1, it's basically going to be 0. And right now, okay, we're going to start from -1 to 2, which is a realistic state space given. Okay, now -1 to 2, what I'm just going to do is I'm first going to go from negative infinity to X, and from there I'm going to go from negative infinity to -1, then I'm going to go from -1 to X. Okay, as you can see what I'm doing now, okay, starting from negative infinity to -1. Of course, that is outside the range given here, and that's why it's going to be 0. Then where I stop here is going to act as the lower bound here, then up to X. Okay, so when I integrate this guy now, I'm actually going to have this guy. Okay, and don't forget, my upper bound is going to be S, and my lower bound is going to be -1, and I'm just going to plug in that, and I have this guy now. Okay, the next thing I'm actually going to do is to consider an upper, the range outside, we are left with S less than 2, but we're going to consider greater than 2 now, which is going to be the next one. But before I go into that, I first want to showcase what I've done here. Okay, we moved from -1, and that actually truncated at X. That's what you are saying, depicting by the graph. okay, but I want to go for s greater or equal to 2. For s greater or equal to 2, automatically I'm actually going to cumulate all the way starting from negative infinity to negative 1, from negative 1 to 2, and from 2 to x. Okay, now of course from negative infinity to negative 1, because that is outside the state space, of course the f of s is going to be 0. That was what I was referring to an s where the other time. Okay, but for negative 1 to 2, of course we can actually perform an antiderivative on this. And of course from 2 to x, okay, it's also outside the range, that is going to be equal to 0. And of course if you take a look at all this, I'm only going to have this guy, so which is this. And of course we actually verify that guy before, that is going to be 1. Now how do we present our result now? Okay, if I want to present my result now, what I'm going to do, I'm going to say, okay, therefore, the CDF is basically going to be this. You consider a situation when s is less than negative 1, we actually call that as 0. We consider a situation where we are from negative 1 to 2, we have this. And lastly, we consider a situation where s is greater or equal to 2, that is going to be 1. And of course, if I ask you the question in exam, this is a way you basically going to present the CDF. Take a look at all of that. Okay, but you know what? The more realistic one is basically the one in the middle. Okay, is the one that actually represents that. Okay, why the one here and here, they basically going to be called an extreme case. Okay, extreme values of the CDF. I'm talking about the one I will call at the tail. Okay, but now if I now want to depict all this is a graphical way to depict that. Okay, if you take a look at all of that, starting from negative 1, there's something start moving, and at the end of the day, by the time we get to 2, okay, 2 and above is basically going to remain flat, because anything from 2 and above is basically going to be 1, since you can never get more than 1. Okay, all of them going to accumulate up to 1. So take a look at all of that. Okay, so how do we now use the CDF to figure out how the probability of S lie between 0 and 1? Okay, since I've already obtained my f of x to be equal to this guy, or what I'm just gonna do, okay, if I have, like I said, I got f of x is gonna be 1 over 9 s to the power 3 plus 1, and I basically want to find that guy. So which means I need to first find f of 1. Finding f of 1 is more or less like plugging in 1, and that's going to be 2 over 9. And f of 0, I'm going to do that as well. 0 to the power 3 plus 1, that's going to be 1 over 9. So you got 2 over 9, 1 over 9. Then we're going to subtract that, and that is basically going to give you 1 over 9 that you are seeing right now. Okay, so the same way that we compute the CDF of a continuous random variable, we can also do the CDF of a discrete random variable. Okay, the CDF is one of a way to identify a particular distribution. Okay, so take a look at what I have now. In order not to create confusion, this guy is basically I'm actually going to call that the probability of x equal to x, okay? Because we're talking about discrete case where the possible values of x can actually be counted. You get what I mean? 0, 1, 2. And of course, these are the corresponding probability of the state of nature. Okay, so how do I find the CDF in this situation? So if I want to find the CDF in this situation, I'm actually going to go against the range. Okay, this is 0. I can consider less than 0. Okay, less than 0, of course, the probability does not exist. Okay, which is going to be 0. Then I'm going to go from 0 to 1. Then the 0 to 1 is basically, when I say 0 to 1, you can see what I have here, right? Okay, which is basically going to be the probability of s equal to 0, which is 10 over 28. Then I'm going to go from 1 to 2. Then I'm actually it's going to be recursive in nature. What I have here is also going to be nested here, plus that. So which means plus that, and that's going to give me that. that. And if I want to do S greater or equal to 2, then this is going to be part of the next one plus the probability of S equal to 2, which means I'm adding all of that up, and that's basically going to be 1. If I now want to present that now, I'm actually going to present it this way. So take a look at this. So this is the way I actually want that to be presented. That is a CDA of the random variable X. And this time around, the random variable X is actually a discrete type. Okay, so if I actually want to have a graphical representation of the scenario now, okay, so what am I actually talking about? Okay, so when you take a look at all this, S less than 0 does not exist. You can say there's no one that we actually started from negative, so it doesn't exist. And when you take a look at, this guy here, okay, you can see it is close here, close at 0, open at 1 is this guy. You can see the dot, okay, you can see the shaded one, and open here. So 0 to 1, of course, that is 10 over 28 that you can see. Then if you come here now, close at 1, open at 2, okay, this is it. Okay, can you see that now? Okay, this is exactly what I'm trying to say. Okay, do you see that now? Close at 1 and open at 2. And then when you take a look at the last one, we basically see S greater than or equal to 2. S greater than or equal to 2, of course, is basically going to be shaded here and going to go all the way, and that corresponds to 1. So take a look at that. So this is the graphical representation of that. Okay, so you may want to, make an inference, computing some probability of values, when you take a look at this, less than 0 means is negative, it could be negative whatever, for negative whatever is going to be 0, whether for negative 0.5 or negative 0.7 or negative 1 or negative whatever, provided the number is less than 0, they are going to be equal to 0. That's exactly what we mean. And if I want to use this now to actually figure out f of 1.5, of course, the f of 1.5 is more or less you are accumulating all the way to 1.5. Accumulating all the way to 1.5 based on what you are saying there is going to be just 1, which is going to be, what you have here. This is the one that included 1. So which is going to be 25 over 28. And of course, if I want to do f of 3.8 now, the f of 3.8 is more or less like the probability of s less or equal to 3.8. And of course, any reasonable, for 3.8 is when you have f of 2, okay, which is basically going to be 1. So take a look at all of that. Okay, so this is actually what I've presented before about the range of values. Now, the next objective that I actually want to walk everyone through now is what we call the expected values. Okay, the expected value is actually the mean. Okay, when you have a random variable S, you remember the other time when we're dealing with a discrete random variable, what do we do? What we do is actually we multiply the probability of X, okay, with the corresponding the X values, and you sum that. You remember expected value of X in a discrete case is basically summation X, okay, the probability of X equal to that over the state space. That was what we did under the discrete. But right now, we're no longer talking about discrete, okay? We're talking about continuous, okay? Now we expect the summation sign now to be replaced by integration sign, okay? And what we basically are going to have, okay? If I want to find the expected value of X, okay, which is the mean of X, okay, it's basically going to be the integral, consider the range of the state space, then X, f of X, the X, okay? You remember that, in a stochastic environment, okay, we normally want to have the idea of the mean, okay? This is how we figure out the mean. So the mean in this case is basically going to be a weighted average, okay? Now, this is an example here. The PDF of weekly gravel sales X was given as this. The mathematicians have already model, the graph, the weekly graph of sales, and that can be written as this. And of course, the range, the state space is going to go from 0 to 1. Okay. Now, when you take a look at what I have, we can actually investigate whether the FFS here is valid. Okay. Now, what we are trying to say here is that it doesn't exist when the range is outside 0, 1. That's exactly what we mean. Now, how do I find the expected value of X? This is the formula. Or what I just need to do, okay, is actually to plug in whatever the given f of X. I'm actually going to plug it in here. Okay, so when I do that, you can see now the f of X is coming in, and I'm just going to simplify, bringing 3/2 out. And when I bring 3/2 out, I'm actually going to use S to multiply this and multiply that. And that is basically going to give this. Okay, or what I'm just going to do now is to integrate this guy, which is going to be S to the power 2/2 and S to the power 4/4. And when I do that, okay, that is what I'm actually going to have. Or what I'm just going to do is to plug in 1. After plugging 1, then I'm going to plug in 0. Then I'm going to subtract that, and that will automatically give me 3/8. Okay, you can revise your knowledge of calculus. That is exactly what you're going to get. Okay, in a stochastic world, anytime, when we get the mean, or how do we tell about the reliability of the mean? Of course, we need to obtain the variance. And from the formula of the variance of X is basically expected value of X squared minus expected value of X all squared. And you know what? We've already found the expected value of X to be 3/8. You get what I mean? Okay, and we want to figure out what is the expected value of X squared. Okay, the expected value of X squared is just going to be X squared f of X dx, and we're going to plug in the values again, the function again. Okay, so when we plug in that, okay, by the time you bring 3/2 out and you use X squared to multiply this and that, okay, and you integrate, okay, and you basically plug in 1 and 0, you're basically going to get 1/5. Okay, so when you get 1/5 for that, then you are set to get your variance. Okay, because you're actually using the formula you're using now is expected value of X squared minus expected value of X all squared. The expected value of X is 1/5 that you got, and the expected value of X is 3/8. Okay, or what you're going to do is just to simplify all of that. That is going to give you 19/320. And you can, in decimal, you're basically going to have this as the variance. Okay, and the moment you get the variance, of course, we need to get a standard deviation. Okay, because if I really want to tell how reliable is the mean, I need a standard deviation. Even though I may not be able to get a standard deviation without passing through the variance. And why is it that we cannot just use the variance? Because the variance is measured in a square unit. Okay, the unit of the variance is different from the unit of the mean, and that is the reason why we're going to find the square root of the variance. And of course, the standard deviation is basically going to be used to tell how reliable is the mean. Okay, so when you find the square root of that now, okay, the square root of this guy is basically going to give you this guy. Recall that, when I have a sigma square x, okay, the standard deviation is basically going to be the square root of that, so which is sigma f. Okay, so that is giving you that now. Okay, so take note of all of that. Okay, so there's an exercise here for you that I actually solved. Okay, this is talking about metal cylinder production. Suppose that the random variable x, okay, is the diameter of a randomly chosen cylinder manufactured by the company. Okay, in this particular company, they measure the diameter, okay, and they realize the minimum values they've been gotten is 49.5 and the maximum is 50.5. And the mathematician was able to generate this as a function, okay, for the, the diameter of a of a metal cylinder. And of course, this is the range that we talk about the other time. And outside this range, of course, is basically going to be undefined. Okay, now when you take a look at what I'm depicting now, it's a graphical representation of that, when you consider the minimum and when you consider the maximum. And of course, just like what I showed you before, you may want to investigate, whether that given function is a valid PDF, or what you're just going to do is to integrate that guy over the range, and automatically, when you get a one, that indicates your PDF is valid. Okay. And you may also want to make an inference where you are not interested in the entire range. You basically want to figure out the probability that the metal cylinder has a diameter between 49.8 and 50.11 mm. Okay. If you basically want to do that, we can actually use the idea of the CDF that we used the other time, which means you need to get a CDF, then you plug in 50.1 and you plug in 49.8. You're going to subtract that, or if you don't want to, which is exactly what I'm trying to do here. If you take a look at what I'm doing here, okay, if you take a look at what I'm trying to do now, okay, that is like plugging in 50.1 and here plugging in, okay, 49.8, then it's subtracting that automatically give you that. Of course, since we're not using the entire range, okay, we expect the value to be less than one. We're only focusing on the blue shaded part. So we're not interested in all of that. So we expect the result to be less than one. So what are we trying to tell the world here? Okay, if you really want to interpret this, you can multiply by 100. What does that mean? 43% of a time, okay, the diameter value will actually lie between 49.8 and 50.1. That is exactly what it means. Okay, so I said something the other time about the CDF. If you want to get the CDF, don't forget, you're actually going to start from the lower part to X. And when you do your calculus very well, okay, so this is actually your CDF. Of course, your CDF is going to be in terms of X. And if you basically want to figure out the probability of X lie between 49.7 and 50.0, all what you're just going to do is where you have your CDF, the S, you're going to plug in 50.0, you're going to plug in 49.7, plugging in 50.0, okay, that is going to be this, plug in, that's going to be all of this, and plugging in 49.7, that is going to be all of that. Don't forget where you plug in that. This is the F of S, right? Okay, it's an uppercase F of S, okay, you plug in 50, okay, into that, automatically this is what you're going to have. You plug in 49.7, this is what you're going to have. Subtracting them, you're basically going to have 0.396, okay, which in terms of interpretation, when you multiply that guy by 100, we'll call it 39.6% of the time we expect the diameter to lie between 49.7 and 50.0. Okay, so take a look at the graphical representation of all of that, okay, that I just defined now. This is the one we just found. Okay, take a look at that. And this is the probability of S less or equal to 50.0. And that's all what we get. Oh my God, that is going to be the end of my presentation today. Okay, initially I said I was basically going to make a video for tomorrow, but you know what, I'm not going to do that anymore because I actually want every one of you to fully concentrate on the independence anniversary celebration. Okay, now until we meet on Wednesday, okay, make sure you stay safe enjoying the anniversary, our independent anniversary, of course. Bye for now, everyone.